Very, very happy to have Dr. Andrew Marshall here. He came up specifically just to give a talk for us. I find that amazing. He came all the way from New York just to be here today, so thanks so much for that. Thank you to the Math Club for funding half of his plane ticket. Thanks also to the ASHC, who's hopefully funding the other half. I have to let them know about that. So, a little bit about Dr. Andrew Marshall. He's originally from New York, and had, he ended up leaving high school early and decided he just kind of wanted to do some traveling, which maybe we'll talk a bit about. As he was sort of traveling around, he actually landed in this really interesting town called Santa Cruz. And when he was in Santa Cruz, he started taking classes at Korea, actually. So one thing led to another. From Korea, he went to UCSC, graduated in 2007, and went on to Cornell and finished up his PhD at Cornell last year. Studies algebraic topology, but that's not the topic for today's talk. We will be having another talk tomorrow at 11 a.m. So the problem is they haven't filled my room request yet, so I don't know where the talk's going to be. So what we're going to do is, if you're interested in the talk tomorrow, we're just going to meet here in the lobby of this building, and we'll find a spot for that talk. So today's talk is more of a philosophical talk, but if you're interested in the mathematics as well, come out tomorrow at 11. Okay. So thanks so much for coming, Andy, and
very much, Brian, for having me here. This is very exciting to get to come and give a talk. I love talking. I love being listened to. And, so I thank you for being here and listening. I was going to speak a little bit about myself and my journey getting to Cornell, but that story takes a while to develop. As Brian mentioned, I left home at the age of 16 and hopped freight trains around the country for about 6 years before I settled down with someone to have a family and got very serious about school. And so that's what ended me in Santa Cruz and now in Ithaca, where I'm teaching at Cornell this year. And hoping to have some subsequent jobs shortly. Anyways, that's me in a nutshell, and I'd be happy to answer more specific questions about biographical information, say after the talk. The picture here is William Thurston. Brilliant mathematician, topologist. He was a faculty member at Cornell. He was a member on my committee, and the mathematical community sadly lost him in 2012 at the age of 65. There are two reasons why his picture is here. The first is because he gave talks somewhat like the talk that I'm going to give today, where he would ask questions like, what is mathematics? He would ask that to a room with faculty members, graduate students, undergrad students, and he liked to discuss aspects of mathematics that a lot of other people don't discuss, and that's like mathematics as a cultural practice, the philosophy of mathematics, and how one thinks about mathematics. These are topics that are suppressed somewhat culturally in mathematics for whatever reason. And so math, the community of math maybe has a bit of a convention, say, for suppressing some of these topics, and also tends to have a reputation of not being terribly effective, right? At least one hears complaints about math teachers and math subjects frequently. So maybe there's a correlation there. If there is, hopefully I can be a force of good in homage here to Thurston. I give this talk. The second reason why he's up here is because in these seminars, he gave problems that he called equalizers. And they were problems that were as difficult for faculty members as for the graduate students, because they were new problems in strange new terms. And when you see something new for the first time, you have to approach it like a child, and you have to ask questions, you have to be confused, and you have to be taken a little bit out of the comfort zone of that which you studied for so long. And so this talk here, if I can get to it, I'm hoping is a sort of equalizer, because I'm considering this a general audience, and yet it's an opportunity for me to develop a couple of subtle philosophical ideas that are interesting to me. So I'll begin with a question, and that question some of you will know a little something about, and maybe some of you won't, and that's, does the square root of -1 exist? Wait, forgive me, back up here for 1 second. The overview here is mathematics as, in part 1, a force to describe. It has the function of allowing us to describe. Part 2 here will be very brief, and it is more or less how people know mathematics and the power of mathematics as a force of prediction, as something that we are capable of drawing predictions from. The third, which I'm developing forwards, is deception, how mathematics deceives us. And so that's exciting for me. I'm building something up, and I will tear it down just a little bit. Okay, so for the description part, I'm beginning with this question. Does the square root of 1 exist? Interesting question, and it's a question that students, I would say, have some difficulty with when they encounter it for the first time. There are a few reasons why students have difficulty. So, what does it mean to be a square root, of course? What it is, we're looking for a number, say on the real line, that when we multiply it by itself, we get -1. We start looking for such a number, we see if we multiply positive numbers by themselves, we get a positive number. If we multiply negative numbers by themselves, we get a positive number, right? -1 times -1 is positive 1. If we multiply 0 by itself, we get 0. So there doesn't appear to be any number that we can multiply by itself to get -1. And yet, there's plenty of literature about this number. So what's the deal, right? What is it about? I'm going to refer to this later, this real line. It's going to be all sort of points that have some kind of decimal expansion on the number line, positive or negative, fractions, or numbers like pi, etc. So that's what this R refers to. Okay, so one answer to this question would be, it is enough for us to will it into existence, to say, we just impose that there is some magical number with this property that when we multiply it by itself, we get -1. And that should be problematic, right? One should resist that. For the obvious reason that it seems like something fishy is going on. It seems like there's foul play. There's also this problem of a square root of -1 representing some kind of quality, some quantity, excuse me. Can you have the square root of -1 gallons of water? Can you have this many people in a room? And of course the answer is no. It's not a quantity, and it's not on this line of quantities, right? This real line is a line of quantities. So the question of whether it's okay for us just to define it, to say here's this number and it has this property, even that has some problems. So for instance, I offer you this diamond, and this diamond, when I add 1 to it, I get the diamond back. And when I multiply the diamond by -1, I get 1. Okay, that's not good. Right, there are problems here. And just because I defined this diamond to have these properties does not mean that I can derive other properties from it. Because indeed, from those two expressions, I can derive contradictions. 0 is equal to 1, sort of thing, right? The second one would lead me to believe that the diamond is -1 if it is a number. The first one, oh, I might say that the diamond was infinity or negative infinity or something like that. Certainly no number on the number line has the property that when I add 1 to it, I get itself back. So, sure, I can put those symbols together and I can say that they're true, but what can I do with that? Can I derive other properties of this diamond? Evidently not if I arrive at contradictions, and I will with such a thing. And so that's exactly the argument that the square root of -1, possibly it's not okay just to define. Possibly it's problematic just to define this number. Okay, so it turns out actually that we can introduce the square root of -1 into a number system, and we maintain a lot of the nice properties of that number system, unlike the diamond that's up here. We can introduce the square root of -1, give it a name, and when we multiply and add, it acts a lot like other numbers. We can divide by it. We can add and subtract it, and these are meaningful expressions we get. Now, I still haven't justified really what it is and how to look at it, and I'm still headed in that direction. But I'm saying that we don't do much harm to the real numbers by introducing this artificial number. We lose order. Square root of -1 is not going to be greater than or less than 1, say. We end up not being able to put down an order where we can tell what's bigger and what's smaller. But other than that, things work. Okay, so how we're going to justify the square root of -1, instead of asking where it can apply, we're going to flip the question on its head, and we're going to ask, where do more mild numbers fail to describe meaningful things? And so what I mean by that is, take a number that's not as wild as the square root of -1, say a negative number, and try to imagine a context where it's meaningless to suggest or offer or discuss a negative number of a quantity. And certainly there are many such examples. The 0 in some system where there are quantities and the 0 is picked arbitrarily, like the Fahrenheit scale, negative makes sense. The 0 is just picked on a line of values. The negative means less than that 0 that's picked. If, on the other hand, we're looking at the Kelvin scale, then this is a temperature scale that starts at 0. Temperature is molecules bouncing around. It's the density of energy from heat, right? It's molecules bouncing around. And the Kelvin scale starts at 0, where all of the molecules are stationary. It is as cold as anything can be. Could there be things that have negative Kelvin temperature? Well, it doesn't really make sense. One would have to justify what that meant. It's not obvious from the definition of temperature, of Kelvin in specific, what a negative Kelvin would be. Number of objects present, only as a placeholder, right? We can make sense out of their a negative number of people in it. Money. Do we have a negative amount of money? Maybe, if it represents debt, right? But still, is that really having a negative amount of money? It's not really, right? It's something else. Although it does fine for describing debt, for instance. How about dimension? We've got a point is zero-dimensional, a line is one-dimensional, a plane is two-dimensional. What does it mean to have a negative dimension? Okay, so what I'm doing here is I'm giving examples that show that negative numbers don't always apply. There are contexts to which negative numbers do not apply. Right? Do we conclude that negative numbers don't exist? We'll get to that. Okay, that's negative numbers. What else? How about fractional numbers? Are there contexts that we can imagine where fractional numbers make no sense, do not apply?
Population.
Population. Okay, this is great. This is a very standard notion because we see it so often. Statistically, it makes sense to say the American family has 2.3 kids or whatever it is. If we restrict that to a single household, it's horrific. And it's not meaningful what it means exactly. So dimension, I mentioned that again, and I have a maybe here because there's actually an area of mathematics that studies shapes and spaces that are in between dimensions. And no, that is not a notion that makes sense all on its own from the get-go. It's something that has to be justified. It's not merely that there's something in between a line and a plane that's 1.5 dimensions. It's much more difficult than that. How about iterations of a function or a process or an algorithm? Sometimes when we discuss an algorithm or a process, we want it done immediately and completely. And it doesn't always make sense to say we perform something 1.5 times. I'll give some examples here. Here's a function. It takes in a positive whole number and it splits it in half if it's even, and multiplies it by 3 and adds 1 if it's odd. This is a very fun example because it's famous. And it's called the collapse function. I'll give you an example here. 13 is odd, so we multiply by 3 and add 1. We get 40, 20, 10, 5. Right? It splits in half until it gets odd again. And we multiply by 3 and add 1. We get 16. And then 16 goes all the way down to 1. 1 is odd, goes to 4, right? 4, 2, 1, 4, 2, 1. So it repeats in that little cycle of 3 numbers, 4, 2, 1, 4, 2, 1. It is not known to this day whether beginning with a number will end you at 1. It is not even known if you will necessarily end up in a cycle. It is not known if there is possibly an infinite, non-repeating, ever expanding, ever getting larger sequence for this function, for a function so simple as this. This is an open problem. Anyway, what does it mean to do this function twice, or 2.5 times, or pi number of times, or square root of 2 number of times? It doesn't make sense, right? So I'm challenging the notion of fraction, and I'm saying not even a fraction applies in all contexts. There are contexts where it's meaningless to ask for a fraction that it describes something. Here's another fun example. There's a little game where you take Wikipedia and you click on the first word of every page. And it's changed a few times. I think people have purposefully changed it, but for a long time, and probably today, you will arrive at the word philosophy. The page for philosophy in Wikipedia. And the reason, of course, is because everything is described in more general terms. So if you look up society, or you look up physics or something, you get is a branch of science, right? And science is going to be the first one. Science. What is science, right? Like you're a kid playing this game and asking why. Everything that comes up. Anyway, this is a process that's well defined once we decide on a site, like Wikipedia say, or the internet itself. So long as pages have links, it's well defined. What does it mean to perform this 1.5 times? Okay, just another example. I give you a third example. Doesn't seem mathematical, but, and maybe in some sense it is, and maybe in some sense it isn't, but certainly it's not something that makes sense to do 1.5 times. These are all examples. Rational numbers are not as robust as one might think. So now that we've done this with negative numbers and rational numbers, now I want to go back and say, if there's a context where the square root of -1 is meaningful, then that's where it exists. That's where it applies. That's the justification, the only justification that's necessary. So what I'd like to do is skip over some of this. We might stop and ask, what does exist mean, right, also? Not to be silly about it, right? Not to ask what is, but really what we after if we say that something exists. That's part of the sentence, part of the question is the square root of -1 exists. And the answer that I'm most satisfied with are that math objects, they are simply relationships. They are observed relationships, or they are hypothesized relationships. And they're very simple. Something is greater than something else once we recognize a quantity, right? Once we recognize what an object is, we can count those objects. Very simple relationships. Now, there is a form, there's a branch of mathematical philosophy called Platonism, which says that math forms are sort of perfect and exist in their own form and can be studied in their own form. And I would contest against that math objects need instances. We can study the math object intrinsically, we can find qualities of that math object, but it needs to have instances. You cannot describe 2 without referring to something, even if that something is abstract. Even if that something is merely just a symbol, which is enough, it's an instance in some sense. To name something is an instance. So do math objects exist sort of on their own in some sort of perfect realm that we refer to? And I would say no. They come from a little bit more empirical. They come from relationships that we see over and over again. Okay, so here are a couple of examples. 2 physical objects, 2 repetitions of a process. We've talked about scaling by 2. These are all different. They're qualitatively fairly different manifestations of 2, right? But they're relationships. You recognize 2 objects, you've collected them, you're referring to them. So there's a relationship there. Now, A being bigger than B, there are many contexts where that is meaningful and it's a relationship that's mathematical without even giving quantities to A and B, right? So for instance, height of a couple of people, say, or whether an event happened before or after another event, or ranking of teams or something like that. So these are different. They're different instances of this A being bigger than B, and none of them is like this pure form. But all of them, in all of these contexts, you have that there's this meaningful expression, that this is more than this. Okay. So what am I saying here? I'm saying that 2 doesn't exist floating off somewhere. And why am I talking about that? Because I'm talking about the square root of -1. And I want to say, if we can find an instance where it describes the way 2 describes all of those situations, the way A is bigger than B describes all of these situations, we can find a situation and describe something with the square root of -1, and that's all it needs to exist. Right? Okay, so that's what we're going to do. We're going to see that we can, so R up here is our real line, and I'm claiming that math objects exist only so far as they're meaningful descriptions. Whenever we find that property, we find that relationship amongst objects, then that's where it exists. So we could start with the real line, and then we could say, in fact, there are real lines worth of ways to scale. We just scale the real line. So that is, we can multiply the real line by a number, and it's going to scale, right? We can multiply it by 0, and it's going to scale everything down to 0. We can multiply everything on the real line by 2, and it's going to dilate the real line by a factor of 2, right? We can multiply everything on the real line by -1/2, and it's going to reflect the real line and contract the real line by a factor of 1/2. It will be scaling by 1/2 and a reflection. And we can see that when we follow one scale with another, that is, we scale by A and then we scale by B, the effect is what? What's the effect? What's the overall scaling that happens if we scale by A and then scale by B?
There's an order.
And say louder. B and A times B. A times B. The product. Yeah. We multiply. We're effectively multiplying these numbers when we follow one scaling with another. Right? So if scaling in succession is multiplying, and we're after a context where there's a number that we multiply by itself to get -1, then maybe what we're after is a way to scale the real line so that if we do that twice, we've reflected it, right? Because multiplication by -1 is a reflection, and if we're after the square root of it, we're after something that we can scale by twice in a row and get reflection. So this is the way to think about this sort of thing, right? Not just be handed a definition and say, okay, it makes sense to me, it's easy, it's square root of -1. But we want to think about this in a way where it becomes natural and meaningful and useful. Okay, we could also just ask in general if there's a function that we do twice. That is, some process on the real line. We do it twice, and we end up getting -x. I wasn't sure of the answer to this, say a week ago, but it's not too hard to produce a function, such a function. Well, it's a little tricky, but anyway, they do exist, but it's certainly not scaling the way we do. Why? Because we've already said if we scale by something negative, we reflect. If we reflect twice, we come back, right? If I multiply -2 by -2, I get a +4. So there doesn't seem to be something that we can scale by, do that twice in a row, and end up with reflection. So then, the next thing that I'm going to do here is place the real line into a plane. And now I'm going to ask, is there a way that I can sort of half reflect? Because that's from master. to this number here. We get to this number, but I want to do that by an intermediate process. And so I look at this for a while, I think about this, and then I say, how about a rotation? How about I rotate the plane 90 degrees, either clockwise or counterclockwise. I pick a direction. Now if I do that twice, I get reflection. Right? So I take X, I put it up here, now it's in the plane. And I can rotate the whole plane. I can take X and put it up here. And whatever that becomes, it's just a point in the plane. And now I do that twice, and I've reflected the line. Right? So this is scaling by this square root of -1. It doesn't exist on the real line, but it does exist in the plane. It does exist in this context in a very simple way once we consider the line sitting in the plane. It's merely rotation. Does the square root of -1 exist? If rotations do, then it does, because it's a rotation. And is that by definition what it is? No, but that's an instance. That's a meaningful instance of it. The same way two objects are a meaningful instance of two. Other conclusions here that are a little bit more general. I am trying to put forth that there's a descriptive power of math, and that's where we can observe a system and we can come up with a description of the relationships in that system. And we can build a vocabulary, and that's fun and meaningful and useful and an artistic endeavor as well. So, let alone the power of math to predict, say, or to calculate. Just the power to describe is something. And also I'm saying here, math objects exist only insofar as they are recognized. If they are merely relationships, then one merely needs to observe them, recognize them. Okay, prediction. I'm going to go through this one very quick, and the reason is because the idea here is math as you know it. You take a system, observe the rules, abstract some formal rules, that is, come up with some symbols that mimic the thing that you've observed, right? And now explore that formal model. That means push the symbols around, manipulate them in a way that is part of the game of the formal system. And then you find these hidden phenomena. You find a calculation that seem to go against your intuition, right? There are all these wonderful sort of paradoxes in probability where there are gambler's fallacies. There are ways of setting up experiments where most humans are not rational. They're not optimal in their intuition probabilistically. How do we know that? Well, because the rules of probability are very simple. We can formalize them, we can study them, we can calculate, we can come up with answers, and we can come back and say, actually, you should switch doors in the Monty Hall problem. Okay, I'm not going to get into it, but the point is that in so many, the reason why we all say that mathematics is so useful is because it has this power of being capable of predicting, right? Predicting, I'm using that word very generally. I'm saying when you come up with an optimal strategy, you're predicting something about the real world. You're predicting the way to make the most money when you next sit down at that blackjack table or whatever. I have projectiles and satellites up here because that's a very classic area of mathematics where knowing how a trajectory of something, a cannonball that's shot, knowing the angle to set that cannon up is going to end up being useful historically, back sometime. So the mathematics that describes these is, for number 2 here, is calculus. And the predictions, I'm calling calculations predictions, right? Because we're allowed to do them on paper and then go back to the real world and either see if it works that way or if it doesn't. Black holes, very interesting example of a physical phenomenon that was predicted from a mathematical model. We did not observe stars collapsing into such a density that light cannot escape before we predicted that such most likely existed. And that's powerful, right, to be able to do that. So these I'm looking at all these as predictions. Predictions on how traffic is going to be terrible if we introduce a third bridge or something like that. Right? Predictions. Good to have. Okay. And now this is the part that I think is really fun because I get to destroy something. Okay. We have in mathematics this line that I've drawn up here. We have points that we come to. We should be bothered by as children when someone tells us that this is a point. Right? This represents a point right here. This thing right here. This is a point, right? It looks pretty messy to represent a point, but even this, if I'm to zoom in on that, this thing's going to look like what I just drew. So, and I'm supposed to look at that and think there's like the head of a pin, but smaller, infinitesimal, tiny, right? So small that I can't scale it to make it larger. It's just a location, a perfect location. And that's what this line is made up of. And that's common. That is the way mathematicians look at this. It's very simple once you come to terms with it, and it's taken for granted, right? And it's deceptive because we don't have that in the real world, and we know that we don't have that. Maybe the Greeks did not know this, but we do. We know that things get very strange when we zoom in far, and we know that we do not have any tools that are infinitely precise. We cannot specify perfectly almost any of these points on this line. And yet we've got this model that's like ubiquitous in science. It's everywhere in science. That is the mathematics of this line, with points of infinite precision. So I already said things exist if they're meaningful, right? And now I'm going back against that a little bit. I'm saying, well, okay, the points on the real line, they are useful, and so they're going to exist in the way of part 1 of this talk. But they don't exist in a physical way. They don't exist in a meaningful physical way, a point, right? Approximations exist. The observations we make are approximations. They're not precise. We take this line and this plane and imagine that we live in a 3-dimensional space that's much like this, right? And we denote that with that little 3, and we might consider time to be a 4th dimension. And if we do that, we might consider that we live in a 4th dimensional space. Space-time, right? But we don't live there. We don't live in this realm where infinite precision is possible. We don't. The universe does not work that way, so far as we observe. And this notion of scaling also is something that doesn't actually physically exist. It is a bit of a fiction. So at a macroscopic level, you can scale. You can know someone that is twice as large as someone else. You can know of a car that is twice as large as another car, right? if you count the number of atoms, if you're capable of counting the number of atoms in these two objects, one of which is made of the same thing but is twice as large, you're going to find twice as many atoms, right? So scaling, in the mathematical sense, doesn't work at the atomic scale. So I have here two different ways to scale. I've got this little object up here. I don't know what it is. Here I've scaled it in whatever drawing program I was using. It's very easy. And here I just redrew it with more of the same little particles. So the kind of scaling that we understand when we say this car is too small, I want to upgrade to a larger one, is going over here on the right. Right? You're picking something that's more, that has more resolution. You're picking something with higher resolution. You get something that's larger. And yet the mathematical scaling tells us that this is what's happening, right, at every scale. And that what happens at the atomic level, or the subatomic level, is you can take hydrogen, which just has a single proton and a single electron, and you can say this is what it is. It's like a tiny little moon going around a planet. And then you can ask, what does it mean to scale this, right? To the right, we're changing hydrogen to helium. Right? Now we have helium. Different chemical properties. Over here, we scale mathematically, we end up with big hydrogen. I just made this up. We don't know anything about it. And not only do we not know anything about it, it's almost meaningless to ask the question of what chemical or physical properties would it have. You come home from work one day and you walk in and there is a giant proton in your living room. You know? And you shine a flashlight on it, you poke it, you do all these experiments. You turn the stereo on, see what kind of music it likes. We don't have any kind of prediction. We don't have any kind of prediction for what. It's not even a meaningful question, because what does it mean to scale? As far as we know, protons are the same size, they're at the same level. So we can have no idea of how our own matter, that is made up of very tiny protons, would interact with this scale proton, right? That's something that's interesting. So we don't have a general theory of matter that's so robust that we can scale mathematically. And scaling is a very, very simple mathematical procedure. And totally dubious. That's the point here. The other thing to mention is that physics is not scale invariant, right? So that means we wouldn't expect this to have the same properties as this. When you look at insects, or you look at bacteria under a microscope, you see radically different structures than when you look at megafauna like camels and elephants and whales, right? If an ant were scaled, it would not be able to hold itself up. It would have these spindly legs and this massive abdomen that would crush buildings, and it would not be able to hold itself up. And so the reason why structurally you see so much difference, say, from elephants to ants, is because the physics doesn't scale. And there's an explanation for that in terms of strength being a cross-section, strength being proportional to area, strength doubling when you scale everything, whereas mass is proportional to volume, to cubing when you double everything. So when we blow something up in our scaling operation, we end up with a giant that can't hold itself up. Right? So the physics is different at different scales. If it were not, imagine that for a moment, that's fun. If physics were scale invariant, then you would have objects, you could have objects at every conceivable level. It would be very difficult to measure things. You would have one ruler, and the tiny little microscopic people would have another ruler. And you could get together and agree that your ruler was 1,000 times the size of theirs, but if this existed at every single scale, then how do you differentiate scale? You're just in this endless, you can compare. You can compare. There's not really any absolute scale anymore, right? But this is not the universe that we live in. This is not the way things work. What about time invariance? That is, what if physics worked at different time scales the same? So you have a watch, someone else has a watch that goes much faster, and people are flying in and flying out, and someone is like stuck, always trying to get to that door, because the same process is happening on totally different time scales. Right? That would be maddening. It's not the way things work, though. We can depend on certain chemical processes at certain scales and at certain time scales, and that's what allows us to measure. Right? So this is all interesting and fun to talk about, but what I'm after here is that scaling is a fiction. Points are a fiction. The universe as we observe it does not corroborate the existence even of scale. Okay, this one I left to your imagination. I got skilled at animations. In consequences, physics is not scale invariant at any scale. This sounds kind of circular, but either it's scale invariant and therefore at all scales, or it's not scale invariant, and therefore it can't be. You can't zoom in far enough to where it becomes scale invariant. So one might guess that physics changes radically at different levels. So I would like to put forth this idea that these very most basic properties, say of matter, like shape, location, size, the very building blocks of a theory of physics, don't always apply. They're possibly, at least, they break down and become meaningless at certain levels. One way to justify that claim is to say we live in a computer simulation. It's just a crazy hypothesis, right? That a franchise of movies made quite a bit of money exploiting, called The Matrix, of course. But and the idea goes back much further than that. But the point is, if we did happen to live in a simulation, then location itself and size break down to a certain level, right? Because if what's simulating you is just a program, some discrete program somewhere, some finite sort of program, then you can't ever divide something physical. At some point, there's no reference for that type, right? Because the program itself doesn't have infinite precision. So this is interesting. The very building blocks of a physical theory, the contexts at which they go down. And this whole idea of there's a children's book called Miss Frizzle, and she's got a magic school bus, and she takes the magic school bus lots of wonderful magical places to learn about science. And one of the things she does is her school bus will shrink down, and she can explore things, by getting on a radically different scale, on a totally different physical scale. But that's the notion that a lot of us have been taught about, say, atoms or even subatomic particles, that you could what would it be like to stroll along the surface of a nucleus how far away would the electron look to you, or something. And sometimes those questions are meaningful, but sometimes they're misleading. They're misleading in the sense that that an atom, or the things that make up an atom, they're not physical, rigid bodies in the way that we know, like a table or a brick is, right? Because they interact only with each other, and they interact then with us at a very asymmetrical scale. And this here, I've already said, the bad news, we do not have a general theory of matter in which scaling makes sense. That's profound and devastating at the same time. So I'm just about done here. I want to leave this question up to you, but the idea from what I've developed so far is to think about, for instance, a universe where there's no such thing as a liquid. And so it's pretty easy to imagine such a universe. Robots, right? Just with that breathe air and are made of solid. And you look through a magnifying glass and you find on a little pebble what resembles an ocean, right? A little puddle, a tiny little piece of liquid or something like that. And you can do tests. You can interact with your whatever tools you have. You can test that. But when you're going to describe that to other people, you have a problem. You have a problem that you're trying to relate liquid to solid and gas, and that's difficult to do because you need a sort of shared context to describe something. So I think the right way to think, and it's a totally ignorant way to think about physics, subatomic physics, but the right way to think about it is with this open mind that it's funky and wild at that level and exceptionally difficult to make sense of in terms of our intuition, our macroscopic intuition at this level. And I'm ending here with a list of facts, and some of them we know to be false, and some of them a young physics student will tell you are true. Oh, that's true. And end of story, right? Everyone knows that. Everyone read that in the first chapter. But they are, now you can look at them with suspicion. You can say, okay, maybe it's useful to say that neutrinos exist and travel faster than light. And maybe there are experiments that corroborate that. But you want your facts to be shorthand for predictions. You want your facts to be shorthand for what you expect experimentally, and not some platonic, perfect value of true rather than false sort of notion, if that makes sense. I'd be happy to answer any questions if there are any.
What kind of harm and what do you mean by do harm to the numbers?
Okay, yeah, good question, but I guess really what I meant by that is that this diamond that I suggested with these very strange properties, if I still allow myself to add and subtract and cancel things out and stuff like that, and I'm able to show that 0 is equal to 1, then I'm in trouble. Because from that, I can show maybe that any two numbers are equal, and I sort of lose a lot of sense and power of what that system is capable of doing. And so that's the only harm that I mean. We expect that our system is consistent and doesn't break down. Yeah.
many years from start to finish did it take for you to earn your doctorate degree in mathematics?
It took me a very long 7 years at Cornell, but I was at UCSC for 3 years as a transfer student from Cabrillo, so I was at Cabrillo for 2 years, and strategically stayed at UCSC for a 3rd year so that I could amass a number of graduate courses and get some good letters of recommendation. So that's, how many is that altogether? That's 12 years. Yeah. From scratch, right? Yeah. Yeah, Brian.
So, could you talk about the RU that you did? What is an RU? Maybe start what you did and what people about
Well, so REUs are research experience for undergraduates, and they're projects that range from being cutting edge and very difficult, where you break off a little piece usually under the guidance of a faculty member. Anything from sort of cutting edge to just exploring something, and the research part, the R part, generally means you're looking to publish something out of it. You're looking to at least find a new way of looking, a new way of something, some new result. But yeah, as far as like difficulty, they run quite the gamut. The only REU that I ever participated in was research under a specific faculty member, and it was just me working with him. And I did some programming to help substantiate some conjectures that he had. Well, actually, I did. I mean, the research showed that the conjecture did not hold. But so yeah. Yeah, it's great if there are opportunities here, for instance, working with yourself. I would encourage it. Yeah.
So,
Yeah.
I was going to say just thinking about that one, I guess you said a function that is reflected after 2 iterations or something?
Right.
Like would you say like taking a derivative of sine be an example of it? Or,
Sure, but that's
but it's not,
so that's a function of functions,
specific.
right?
Okay.
That's a function of functions, and you do that twice and you get negative. There's a really close connection between sine and the square root of -1. In fact, that's yeah. One way to look at the plane, when you pick a point in the plane, you've got a distance to that point, and you also have an angle. And you can think about the distance as being the amplitude of a wave, and the angle as being the phase shift. That is, you shift the waveform moves, and it eventually comes back around to itself. And so in that way, yeah, those two things are very closely connected.
I have one follow-up. Is there one bit of advice you would give to someone looking to get a PhD in that?
Yeah, just stay interested, or do something else. I mean, just fall in love with it, and don't be discouraged. There are a lot of strange personalities in mathematics, and if you really love the mathematics, then you find it's a great place. It's a wonderful place to be.